In this lesson, we're going to talk about the derivative function. We've already talked about the derivative as the instantaneous rate of change and also the slope of the tangent line or of the graph. And so what the derivative function will end up being is a function that gives the value of the derivative at any given value of x. We'll start off with some quick estimations. We're going to estimate the derivative of this function by using these tangent lines. And just like I mentioned in the last lesson, this is not a huge deal to be able to do. We're just going to use it as an example. At -2, we're looking at this point, and here's a decent guess at the tangent line. This tangent line has about a 4.5 slope. Then we'll move on to -1, which is at this point. We'll guess that this one is about 1.5. And then we'll go to 0. At 0, you're going to have a negative slope. Something like this, which I'll estimate to be about -0.8. Then at 1, we will say this one is about -2. Then at 2, I'll say this one's about -2.5. At 3, I'll say this one's about -1. At 4, I'll say this is about 0.8. And at 5, let's say this one is about 3.5. Now, what is the purpose of this? What we're going to do is draw all of these points on a graph and see what the graph would look like. On this slide, I'm going to take all the values from the table that I just had. Here's the plots of all the points that I got from the previous example. Let's just try to connect these with as smooth of a curve as possible. Here would be a respective graph of our derivative function from the function we had in the last slide. Everything's a little stretched out, but it's the same function. Now, I want to make a little comparison here. Notice that when this function hits a high point, if you look down at the derivative function, that's where the derivative crossed the axis. Same thing at the low point. The derivative crosses the axis there as well. So it really does give a function in its own right. If we see f prime of x, we'll call that the derivative function, and plugging in any value gives us the derivative or the instantaneous range at that given point. Also notice a few things. When the original function was increasing, the derivative was above the axis. When the original function was decreasing, the derivative was below the axis, and then it switched back to increasing and went above. That's true in general. When you have an increasing function, the graph of the derivative will be positive, meaning above the x-axis. When the function is decreasing, the graph of the derivative will always be negative, which is below the x-axis. And if the graph ever flattens in an area, or possibly maximizes or minimizes temporarily, then the derivative will either touch or cross the x-axis at that point. Finally, while we won't run into this one very often, the graph of the derivative would be 0 if the function was constant right there. Now let's do a multiple choice question on this. Which of these graphs represents the derivative of the function? What you want to do is look at the places where the function seems to flatten out. These 2 points. I'll say this one is at about -0.7, and this one is at about 2.2. Where that happens, you would expect the function to cross or at least touch and turn at the x-axis. With that said, I can actually eliminate one example. This one crosses at -2, 1, and 3, and you really only need to cross at -0.7 and 2.2. Now for the next part, let's consider what's going on with increasing and decreasing. Notice the function starts by decreasing, then switches to increasing, then goes back to decreasing. That means my function should start negative, switch to positive, and then switch back to negative. There's really only one function that does that. This one. On the other one, we have positive, negative, positive, where it should have been negative, positive, negative. Just writing that down for reference, we do have that it's positive and above the axis where the function is increasing, and it's negative or below the axis where the function is decreasing. Now let's do an example of trying to sketch the graph of a function just given the function itself. Again, the first place to look is look for the places where the function is maximizing, minimizing, or at least going flat. These places will be the places where the derivative is 0. And then you just look at it this way. Where the function is increasing, like at the beginning, the derivative should be above the axis, or positive. So I'm going to draw it like this. And then where the function is decreasing, the derivative should be below the axis. But it is going to come back where it was supposed to have a 0. And then where it's increasing, it's again going to be above the axis. And then finally it's decreasing again, so it's going to be below the axis. These problems take a little bit of time to master, and there might be a bonus question on a test where you need to be able to do this without actually using a multiple choice problem. What if we want to make a derivative based on a table of data? Well, what we would do is use that shortcut that we've used repeatedly by doing the one to the left and one to the right, or in the case of an edge, you might need to just pick one on that direction. So the calculation for c prime of 0 would use 0 and 0.1. When we do that, c of 0.1 is 0.89, c of 0 is 0.84, and then we'll subtract 0.1 minus 0. That comes out to 0.5 for this one. And then for c prime of 0.1, this one's not on an edge, so we'll actually do the value to the right and to the left of 0.1. That comes out to 0.94 minus 0.84, all divided by 0.2 minus 0. If you do that, you again get 0.5. Now, it won't be the case every time, but we did get 0.5 again. For c prime of 0.2, we'll do something similar. I get 0.98 minus 0.89 over 0.3 minus 0.1. That comes out to 0.45. We can use a similar process to fill in the rest of the table. Now for c prime of 1, I do want to highlight exactly what's going on there because it's again at an edge. For that one, the best we're going to be able to do is c of 1 minus c of 0.9 over 1 minus 0.9. For this particular one, we get negative 2.2. For our last example, let's see if we can guess at the formula for the derivative of a function just as the formula itself. And let's do that by taking a few estimates. Remember, when you do estimates, it's going from that number to that number with an increment on it of 0.001. So for f prime of 1, I'm just going to be going from 1 to 1.001 and plugging that into the square function. If I do that, I get 2.001. Let's do it again for f prime of 2. This time I'll be doing 2.001 to 2. In that case, I get 4.001. And f prime of 3 will be similar. For that one, I get 6.001. Now there's an obvious pattern. You could probably guess what your estimate would be for f prime of 4. You'd probably get 8.001. So what is this 0.001? It seems like it's following basically just a 2, 4, 6, 8 pattern. Well, because we're estimating, we do have a little bit of error. So I'm actually going to write this. The first one is about 2, the second one is about 4, and the third one is about 6. So from that, I'm going to be able to just say, well, the pattern is just double what we started with. When we looked at 1, we got 2. When we looked at 2, we got 4. When we looked at 3, we got 6. So it's basically just doing this. F prime of x would just be the double of what we started with, 2x.